there are a few combinations of trig functions and inverse trig functions that are a little bit hard to deal with, but they will figure out that you can compute them if you keep a few things in mind. So the first thing is that trig functions take angles theta and produce x values, y values, and slopes, depending on whether you're talking about sine, cosine, or tangent. And inverse trig functions go the other way. They take either x values, y values, or slopes, depending on whether you're talking about inverse sine, inverse cosine, or inverse tangent. And they produce angles as their output. The second thing to keep in mind is, when in doubt, draw the most important diagram. Most important diagram. Okay, so here's our first example. Let's find inverse sine of 7 pi over 12. Well, 7 pi over 12 is not one of those nice angles that I know sine of. So we're going to have to come up with some other way of figuring out what this is. But, you know, we can use these two suggestions. So let's draw the most important diagram. I guess the first thing to check is, since we have sine inside of inverse sine, the first thing to check is this angle that we're starting with in the restricted domain of sine? Because if it is, then we can just cancel the sine and inverse sine and be done with it. Is 7 pi over 12 in this interval? It's not. It's too big. It's a little bit too big. So we can't take the shortcut route here. So we'll have to draw the most important diagram. And the angle that we're working with is 7 pi over 12. 7 pi over 12 is a little bit bigger than 6 pi over 12, which would be pi over 2. So our angle, 7 pi over 12, looks something like this. Okay, and this little excess, this tiny wedge in here, that's pi over 12. Okay, so if we say that this is a unit circle, then sine of 7 pi over 12 is just the y coordinate on the unit circle. So sine of 7 pi over 12 is this y coordinate right here. All right, now we want to take inverse sine of that. Well, inverse sine turns a y coordinate into an angle. So we have our y coordinate. Well, we have a picture of it. We don't know what number it is, but we have a picture of our y coordinate right here. And we want to know what angle between minus pi over 2 and plus pi over 2 would produce this y coordinate. Well, let's extend this horizontal line rightwards. And you can see the angle that would produce this y coordinate. It's this angle right here, this green one. Of course, this doesn't immediately tell us what this angle is, but if you look at the whole diagram, there's some symmetry here. This little pi over 12 wedge here at the top, it's the same size as this little wedge here, so this is also pi over 12. Right? If you just mirrored this image over the y-axis, it would fall back onto itself. So those two little wedges are the same size, so they're both pi over 12. But the angle that we want down here, it's a right angle minus pi over 12. So that's pi minus pi over 12. And that's 5 pi over 12. Okay, so this is 5 pi over 12. So the moral of the story here is that this angle, 7 pi over 12, sine turned it into a y coordinate, inverse sine turned it back into an angle. And we just had to be careful to get the right angle for this y coordinate. All right, let's look at another example. Let's find sine of inverse cosine of minus a half. Now, if this trig function on the outside were cosine instead of sine, this would be a lot easier because we would have inverse functions composed, but it's not, it's sine. So what are we going to do? Well, let's think about what things mean geometrically. So this inverse cosine of minus a half, what sort of things, what geometric quantities does inverse cosine produce? It produces an angle, so let's call this theta, because it's an angle. And what goes into inverse cosine? Well, what goes into inverse cosine is what comes out of cosine, and that would be an x-coordinate over a radius. So we could treat this as we could treat this minus 1/2 as x over r. Well, we can draw a copy of the most important diagram that reflects this geometric situation. So let's do that. So we have a circle. This time, the circle, instead of being a unit circle, the denominators here seem to suggest that we should make our radius 2. So let's do that. And we want the x-coordinate in this diagram to be minus 1. Don't forget that minus sign. So that's here. All right. So we need some triangle that, we need to draw an angle that gives us this, an angle theta that gives us this x-coordinate at minus 1. But remember, theta, because it's coming out of inverse cosine, it has to be in the restricted domain for cosine, which is from 0 to pi. In other words, it has to be in this top semicircle. So to be in the top semicircle and get this x-coordinate at minus 1, we have to be up here. So here's the angle that we are producing. So that's theta. So there's a picture of our angle theta. Now we want to know what is sine of inverse cosine of minus a half. But inverse cosine of minus a half, that's theta. And we have a picture for theta. Right? All we need to do is figure out what is sine of the angle theta in this diagram. Well, it's y over r. And we know what r is, it's 2. So we just need to figure out what is y. We have this right triangle. The hypotenuse is 2. The x-coordinate is minus 1. So we just need to figure out what is the y-coordinate here. And of course, the Pythagorean theorem says that y squared plus our x-coordinate, negative 1 squared, is r squared, and that's 2 squared. So this tells us, if you do the computation and solve for y, you get y is the square root of 4 minus 1, plus or minus, the square root of 4 minus 1. So plus or minus root 3. Because we are in the second quadrant, we know we have to choose the plus. We can't choose the negative. That would put us on the bottom half of the semicircle, because that's where negative y coordinates live. So now finally we know y. It's positive root 3. So root 3 over 2. Okay. Of course, for this particular problem that we started with, minus a half, we could have taken a shortcut because we actually know what angle this is. But the point of this example is that you could do this, you could work out this computation even if this value right here, this minus a half, wasn't so nice to begin with. All right, let's look at a couple more examples. Let's find cosine of inverse tangent of 4/3. Now 4/3 is not a nice value for tangent, so there's not going to be any shortcut using angles that we already know. So let's see. Inverse tangent, what sort of quantities does inverse tangent produce? That produces angles. Inverse trig functions produce angles, so let's call inverse tangent of 4/3, call that theta. So then this means that tangent of theta is 4/3, but tangent is y over x. So this seems to be suggesting that we should draw a most important diagram where y is 4 and x is 3. So let's see, if y is 4 and x is 3, that's going to look something like this. So our circle is going to be something like this. Okay, and our angle theta is going to look like that. Okay, now to calculate cosine of this angle, remember theta is the inside of our cosine function here. To find cosine of this angle in our diagram, we're going to need to know the radius. But as usual, we have two sides of this right triangle, so we can find the third side. So 3 squared plus 4 squared is going to be r squared. And so r squared is 25. And so r is 5. Notice that we don't have to worry about the negative possibility because a radius has to be positive. It can't be negative. So now we know that this radius is 5. And we can use this diagram to figure out any trig function we want. In particular, we can figure out cosine of theta. Cosine of theta is just x over r, and that's 3 over 5. All right. Notice that we did all of this without ever calculating theta, and that's the power of the most important diagram. One more example. Let's simplify tangent of inverse sine of x. So again, this inverse trig function produces an angle. So let's call inverse sine of x, we're going to call that theta. And that means that sine of theta is x. Now this is a little confusing because sine of theta is the vertical coordinate over a radius, and here we have an x showing up. So we're going to have to keep in mind that this x, it's not the horizontal coordinate in our most important diagram, it's just some variable. In fact, maybe it would be easier to temporarily call this something other than x. So just for the time being, let's call this m. Okay. So sine of theta, it's m, but usually we think of sine of theta as being y over r in a most important diagram. And we can choose any radius we want, so just to make things easier, why not choose radius 1? Okay, so we need to draw a most important diagram. And our y coordinate, so the numerator over here is y, that should be equal to the numerator over here, which is just m. So we have some height m, and the radius over here is 1, and that should be the denominator over here. So that's why it makes sense to choose 1 for the radius. All right. Now we have this right triangle. The right side is m. The bottom side we don't know yet. I was going to call it x, but that's a bad idea. Let's call it n, I guess. So the Pythagorean theorem tells us that n squared plus m squared is equal to 1. We can solve this for the unknown, which is n. N is plus or minus the square root of 1 minus m squared. But look, where n is a horizontal coordinate, and this angle is coming out of inverse sine, so we know that whatever angle this is, it's in the right semicircle. So n is always going to be positive, so we don't have to worry about this negative possibility here. Okay. Now that we have a picture of the situation, we can evaluate tangent on this diagram. Tangent is the the vertical coordinate, which is m, divided by the horizontal coordinate, which is n. So remember, m is the variable we started with, so it's okay to have m's floating around. And n, in terms of n, it's the square root of 1 minus m squared. Okay, and that's it. So you can see for all of these examples, drawing the most important diagram really did the trick. So that's why I call it the most important diagram. It's because it gets you out of a lot of sticky situations.